So vast, and there should be so many civilizations. Where is everybody? Why is the sky so quiet?
That's the million-dollar question. Maybe the rare Earth hypothesis is right and the gauntlet of the habitable zone is just too brutal?
But this is the perfect moment to introduce Layer 4. Because everything we just discussed, this massive, towering set of strict rules, the Goldilocks zone, the rare Earth, it might all be completely wrong.
Right. It is entirely colored by our own bias.
Bias?
Yeah.
How? We just spent 40 minutes walking through the hard physics and chemistry.
Yes, but it is physics and chemistry based entirely on looking in a mirror. We are looking for Earth 2.0. We assume that life fundamentally requires a sun in the sky, a solid rocky surface to walk on, and an atmosphere to breathe. Some astrobiologists argue that we suffer from carbon chauvinism or surface chauvinism.
Surface chauvinism. I really like that term. We assume that because we live on top of a rock under a bright sun, everything must live on top of a rock under a bright sun.
Exactly. We built this incredibly rigid mold for habitability. But if there is one thing we have learned from studying extreme environments, it is that nature absolutely loves to shatter our strict rules.
So how do we break the mold? Where do we look?
We don't even have to leave our own solar system. We just have to look past the frost line. We need to talk about the ice moons of the gas giants, specifically Europa, which orbits Jupiter, and Enceladus, which orbits Saturn. We could also throw Titan, Ganymede, and Callisto in there too.
Let's focus on Europa and Enceladus. Okay, if we apply the rigid rules we just established, these moons should be dead, sterile rocks.
They could be completely dead.
No.
They sit hundreds of millions of miles outside the traditional stellar habitable zone. The sun out there is just a bright star in a black sky offering virtually no thermal heat.
They are deep in the freezing room.
On the surface, yes. They are encased in shells of rock-hard ice kilometers thick. The surface temperature is hundreds of degrees below zero. They are exposed to the raw vacuum of space. By all classic definitions, they are totally uninhabitable wastelands.
But they aren't, are they?
They are hiding a profound secret. When planetary scientists sent probes like Galileo to Jupiter and Cassini to Saturn, they took magnetic and gravitational measurements of these moons. And the data revealed something genuinely shocking.
What did they find?
Beneath those kilometers of impenetrable freezing ice, both Europa and Enceladus possess massive, global, liquid water oceans.
Liquid water. Not slush, not ice. The universal solvent we were talking about at the very beginning.
Liquid, salty oceans covering the entire globe beneath the crust. In fact, there is more liquid water hidden beneath the ice of Europa than in all the oceans on Earth combined.
Okay, hold on. We just spent this entire deep dive establishing that you need a star's heat to keep water liquid. If they are so far from the sun that the surface is a solid block of ice, what is keeping the water underneath melted? Where is the heat coming from?
This is the massive paradigm shift. The heat is not coming from a star at all. It is coming from a gravitational engine.
A gravitational engine. Are we talking about tidal forces again? Like the red dwarfs?
It is tidal heating, yeah, but functioning in a spectacular way. Jupiter and Saturn are massive gas giants with immense gravitational pulls. As moons like Europa and Enceladus orbit them, their orbits are not perfectly circular, they're slightly elliptical.
So their distance to the giant planet changes as they go around?
Exactly. When the moon swings closer to Jupiter, Jupiter's massive gravity physically pulls harder on the moon, stretching it out of shape. When the moon swings further away, the gravity lessens and the moon relaxes back into a sphere.
So the moon is physically bulging and contracting.
It is constantly being squeezed and stretched every single orbit. Imagine taking a solid rubber ball and violently squishing it in your hands over and over again. What happens to the rubber?
It gets hot. The friction of the material constantly moving against itself generates heat.
Precisely. This immense internal friction, caused by the gravitational flexing, generates immense heat deep within the rocky cores of these moons. The rock gets so hot that it radiates heat upward, melting the ice from the bottom up.
So the heat isn't raining down from the sky, it's radiating up from the seafloor.
It creates a vast, pitch-black ocean, sandwiched between a hot, rocky seafloor and a freezing ice ceiling.
That solves the liquid water problem without needing a star at all. But what about the other ingredients? Down in the pitch black, under miles of ice, there is zero sunlight. No plants can grow, no algae can photosynthesize. Where does the energy for biology actually come from?
Well, we wondered that too until the Cassini spacecraft made a daring maneuver at Enceladus. Cassini discovered massive geysers of water actually erupting out of deep cracks in the ice at the moon's south pole.
The moon was literally venting its ocean straight into space.
And NASA decided to fly the Cassini probe right through those plumes to sample the water. When they ran it through a mass spectrometer, they found water vapor, salts, and complex organic molecules. But the real smoking gun was the discovery of tiny silica nanograins.
Why is silica important?
Because on Earth, those specific silica grains only form in one place, where liquid water interacts with rock at temperatures above 90 degrees Celsius.
Hot rock and water, you're talking about hydrothermal vents.
Exactly. The data strongly suggests that at the bottom of the ocean on Enceladus, there are hydrothermal vents spewing superheated water, minerals, and complex chemistry directly into the dark ocean.
And we know for a fact that hydrothermal vents on Earth harbor life. Down in the Mariana Trench, miles away from sunlight, there are complete ecosystems, tube worms, blind crabs, thick mats of bacteria.
And they don't use photosynthesis, they use chemosynthesis.
Chemosynthesis.
Yeah, the bacteria extract energy directly from the chemical reactions of the volcanic vents, stripping hydrogen and carbon to create their own food in complete and utter darkness.
So if biology can thrive at the bottom of our oceans on pure chemical energy, there is no fundamental physical reason it couldn't be happening right now in the oceans of Enceladus or Europa.
None at all. It completely shatters the classical mold. It completely flips the script on what habitability even means.
We've been looking for life lounging on a beach under a warm sun, but life might actually be thriving in a planetary submarine running purely on geothermal battery power.
The submarine analogy is perfect. The ice crust acts as the hull. It holds the ocean in, protects it from the vacuum of space, and crucially, it acts as the ultimate deflector shield.
Oh. Because Jupiter puts out a lethal amount of radiation, right?
Jupiter's radiation belts are a literal death zone. If you stood on the surface of Europa, the radiation would kill you in a matter of hours. But water and ice are incredibly dense and fantastic at blocking radiation.
So the ice protects them.
Yeah, beneath a few kilometers of ice, that subsurface ocean is perfectly calm, dark, and completely shielded from the chaos of space.
So what does this revelation do to our concept of the habitable zone?
It forces us to realize that the habitable zone is not a flat, two-dimensional ring around a star. It is a massive, three-dimensional web of possibilities. You don't need a star to survive. You just need an energy source, like the gravitational pull of a gas giant, and a solvent medium like water.
Which really opens the door to asking, do we even need water?
Or carbon.
That is the frontier of astrobiology right now. Could life exist with completely different biochemistry? Like silicon-based life. You see that in sci-fi all the time.
Silicon is right below carbon on the periodic table, meaning it shares some chemical properties and can form complex chains. It's heavier, so the bonds aren't as stable as carbon, but under the right conditions? Maybe.
What about the solvent? If not water, then what?
We look at Titan, Saturn's largest moon. It has lakes and rivers, but not of water. It's so cold there that methane and ethane exist as liquids. You could theoretically have a biology that uses liquid methane as its solvent instead of water.
That is completely alien.
It is. Ammonia is another candidate. Our understanding of habitable environments has expanded so drastically over the last few decades. Every time we think we've found the perfect recipe for life, nature introduces another possibility that just challenges all our previous assumptions.
Meaning there could be billions of icy moons scattered across the galaxy, invisible to us, sitting in the freezing dark but hiding warm, thriving oceans. Or methane lakes.
It expands the potential real estate for life by orders of magnitude.
This has been an absolutely wild, perspective-shifting journey today. Let's do a grand synthesis of the gauntlet we've run.
We started with the universal solvent, finding a place where water can remain liquid.
We looked for the right campfire. Layer 1. You need a star that gives you billions of years to evolve, like our sun, but doesn't blast you with flares or lock you into eternal day and night like a red dwarf.
But distance isn't enough. Layer 2 is the planetary spaceship. You need a rock massive enough to keep its core churning, generating a magnetic shield to stop the solar wind from sand blasting your atmosphere.
And you need a geological thermostat, the carbonate-silicate cycle, to scrub carbon from the air and prevent a runaway greenhouse effect like Venus.
From there, we scaled up to Layer 3, the grand architecture of the Milky Way. You have to park your spaceship in the quiet suburbs of the galaxy.
Right, you need the heavy metals to build a rocky core, but you must stay far away from the lethal supernovae and radiation of the galactic center.
Which highlights how extraordinarily precise the Earth system is, a rare masterpiece of cosmic alignment.
But just as we felt completely isolated by those strict rules, we explored Layer 4, the rule breakers, Europa and Enceladus. Worlds that sit in the deep freeze of space, ignoring the sun entirely, relying on the intense gravitational squeezing of gas giants to heat their hidden subterranean oceans.
It proves that nature's imagination is just far greater than our rigid definitions.
So, where does this leave the search? Are we going to find something soon?
It leaves us looking at an unimaginably vast universe with incredible optimism. The Milky Way holds hundreds of billions of stars. The observable universe holds trillions of galaxies.
Even if the Earth-like mold is incredibly rare, when you roll the dice hundreds of billions of trillions of times, the sheer numbers mean there just have to be infinite targets out there.
And we are actively looking. Right now, telescopes are peering into the atmospheres of distant exoplanets. We are developing new technologies and future missions that will revolutionize astrobiology in the next century.
We are getting closer every single day to knowing if we are alone. I want everyone listening to take a moment today, step outside, take a deep breath, and just appreciate your local atmosphere.
It's easy to take for granted.
It is. Appreciate the invisible magnetic force field protecting you, the gentle rain scrubbing your carbon, and the stable yellow dwarf star shining down on you. We are living on a spaceship that is running absolutely perfectly.
It really is a profound thing to recognize.
But before we let you go, I want to leave you with one final mind-bending thought to mull over tonight. We just explored how life on a moon like Enceladus doesn't actually need a star. It just needs the gravitational engine of a giant planet to keep its ocean warm.
Right. The star is essentially irrelevant to the ecosystem down in the dark.
So, if you don't need a star at all, could the universe be filled with rogue planets? Massive gas giants that were violently ejected from their solar systems during the chaotic pinball game of planetary formation, now just wandering completely alone through the freezing, pitch-black void of interstellar space.
Adrift in the absolute dark, incredibly far from any galaxy or sun.
Adrift in the dark. But if that wandering frozen gas giant happened to take a massive icy moon with it when it was ejected, and its gravity was still squeezing that moon as it orbited, could there be warm, thriving oceans hidden beneath miles of ice, completely alone in the endless dark space between the stars?
A biosphere thriving in the void, completely unaware that stars even exist.
Now that is a thought to keep you awake. Keep looking up, keep asking questions, and keep diving deep. We'll see you on the next deep dive.